Welcome back. In order to make valid conclusions from data, all statistical methods must be used appropriately. In this video, we'll examine the conditions that are required to use linear regression and how we can check whether they hold for our data. Before fitting a line to our data, we have to consider whether a linear model makes sense to describe the relationship between y and x. If it doesn't make sense, then our square doesn't make sense, predictions don't make sense, and there's no point fitting a linear relationship to the data. We've seen examples where a curve would be more appropriate, and examples where an influential point changes the nature of the relationship. In these cases with an influential point, a model that either doesn't use or accounts for the influential point would be a better choice. Sometimes the data come in groups, and rather than one model to explain all of the data, it would be better to model each group separately. We've also seen an example where subtle deviations from a straight line pattern show up more clearly in a plot of the residuals. So, before fitting a regression line, we should examine a scatter plot, and if, like this one, a straight line model seems appropriate, then we should fit a regression line and follow it up with a residual plot to make sure that there aren't patterns that we've missed. Hopefully the residual plot will look like this one, just like random scatter, and a linear model seems like a good choice. In order to be able to carry out inference on our slope, we need additional conditions. The first of these is that observations must be independent. This is the most important assumption for inference, as there is no getting around it without moving to more sophisticated models. But in general, it's also the most difficult condition to check. Here's an example of how independence might not be true. If we were measuring the crawling age of babies, we wouldn't want to include twins, as we'd expect the two twin babies to have similar crawling ages, so then they wouldn't be independent. This example of CFC concentration versus time has another version of lack of independence. The curved pattern in the residuals here is partly a consequence of the fact that measurements were taken over time, and measurements close together in time tend to be correlated with each other. This is called autocorrelation, and when it occurs, observations above the line tend to have surrounding observations that are also above the line, and observations below the line tend to have surrounding observations that are below the line. Knowing that the data were collected over time would help us catch this lack of independence. Generally speaking, the best defense against incorrectly treating data that are not independent as if they were independent is to understand the data and how they were collected. There are two more conditions that must be met in order to carry out inference on the slope using the methods that we've studied. Recall that our model is a straight line plus random noise, denoted by epsilon. As an illustration of the model, we have a line and probability distributions around it, representing the random distribution of the error terms, which shows how our data are randomly scattered around our line. Implicit in this model is the condition that the variation in the error terms is constant. That is, the variability with which the points are scattered around the line is the same regardless of the value of x. Or in other words, the spread of each of these probability distributions along the line should all be the same. A typical violation of this condition looks like variability that increases or decreases with x. Here's an example with increasing variance. This plot shows data collected from the nutritional information for 77 food items that were sold at Starbucks in the US in 2011. At that time, the display in Starbucks restaurants listed just the calories and not the other nutritional information. We're interested in learning whether the calorie count is a good predictor of the amount of carbohydrates in the food items. The scatter plot shows the amount of carbohydrates in grams on the vertical axis, and on the horizontal axis, it shows the number of calories. From the scatter plot, there appears to be a positive relationship. That is, higher calorie counts are associated with foods that have more carbohydrates. But the scatter plot also shows increasing variability in the amount of carbohydrates, with greater scatter for foods with higher calories. This increasing variability is also seen in the residual plot. And like nonlinear patterns, increasing or decreasing variability is often exaggerated and more easily seen in the residual plot. This pattern of increasing variance would mean that it would not be appropriate to carry out inference on the slope of the line for these data. Our confidence interval for the slope uses a quantile from a t-distribution. And when carrying out a statistical test for the slope, we use the t-distribution again to calculate the p-value. Underlying the fact that we use a t-distribution is the fact that we're assuming that our estimator of the slope is normally distributed. And this will be true if our error terms are normally distributed. Typically, this condition is checked by looking at a normal quantile plot of the residuals. Our residuals should have a normal distribution with a mean of 0. For the Starbucks nutritional data, the normal quantile plot is generally straight. There's a slight curve away from the line at the right end, which is an indication that the distribution of our error terms has a slightly light right tail, a little lighter than we'd expect from a normal distribution. Unlike the non-constant variance that we observe, this isn't a serious concern for carrying out our inferential procedures on the slope. When all the other conditions hold, but we have a normal quantile plot of the residuals that doesn't follow a straight line, then the inferences we could make could only be considered approximately correct. In summary, here are the conditions that must be satisfied in order to use linear regression sensibly and carry out meaningful inferences for the slope.